Hello everybody, hello enthusiasts of IoT. Today we will talk about sensors and actuators that we can use in our IoT devices, IoT systems. You can use them in or together with the microcontroller boards or with the system on chips I shown you last time. So let's go with sensors and actuators. What will we talk about? First, the group of different sensors. So how can we measure different phenomena, different parameters of the environment that we want to check, and how to convert it into the digital value. And after this, actuators, so how to influence back the parameters in the environment. Let's start with sensors. Sensors we can consider as electronic elements or electronic systems, subsystems that are used for measuring, detecting some physical phenomena, some physical parameter that appears in the environment. And we can have different sensors for different phenomena, and also these sensors can be connected in variety of ways to our microprocessor. So let's start with talking slightly about these interfaces. We can have analog interface, so it means that sensor generates analog voltage at the output, and we need to measure this voltage in our microprocessor or microcontroller. It must be equipped with the analog to digital converter, but many of microcontrollers, many of system on chips incorporate such converters, so it's quite easy to build such circuit. This sensor can also be connected using binary interface, and this binary interface or digital interface can use digital values like 0 and 1 to be read. So we have binary sensors, simple 0-1 information like switch on and off. We can have some much more complex communication like UART, so this is serial port. We can have some synchronous serial communication like I2C or SPI. We can have also some other possibilities like one wire or similar to one wire protocol. Let's start with simple binary sensors. Binary sensors, as we said at the beginning, just gives us simple information on or off. Switched on, switched off, active, not active, 0 or 1, high or lower level of the voltage. These sensors can be push button, for example, it can be switch, it can be the full keyboard or simplified keyboard. And few words about push buttons and switches. Push buttons and switches normally we connect to inputs of our microcontrollers, so to GPIO, general purpose input output. This pin must be connected as the input pin, and here on the picture you can see two possibilities of connecting such push button or switch. One possibility is to connect our push button to the ground. One is connecting our push button to power voltage. Of course, this power voltage must be the same as the microcontroller. There is a need to connect this additional resistor or activate this resistor inside microcontroller, but there must be such resistor at the input. If it's not, we have if the button is not pressed, we have some, we can say, unstable situation here, yes, because this input is not connected to anything, so it creates unstable situation, and the information is unclear. So we need to avoid the situations because the state on the input can change depending on the charge, electric charge is that is in the air even. So Be careful about it and always connect or always activate such pull up resistor or pull down resistor depending on the connection of this push button or switch. Another possibility, if we need more information to be provided to our microcontroller, we can use keyboard. This keyboard can be keyboard for the user. This keyboard also can be set of switches or set of push buttons that we have in a bigger system. And if we have not so much inputs as number of switches that we need to connect, we can use such connection like matrix. In this keyboard, keys or push buttons are connected in rows and the other pin in columns. So the schematic diagram of this keyboard can look like this, and the reading procedure of this keyboard is operates like this. We activate first row, so we put, for example, 0 state here and 1 state to another pins, and we read inputs here and we observe if any of the input is low or not. If it, for example, this input is low, it means that this button has been pressed, because here 0 state goes through this button from output to input. And of course, after reading the first row, we need to activate second row, read the second row, next read third row, fourth, and so on, so on. This procedure must be done repeatedly to be able to read all keys, all push buttons in the keyboard. This is quite often technique used even in PC keyboards for reading many keys, many push buttons with lower number of GPIO pins. So this was about digital simple binary inputs. Now, few words about light sensors. Light sensors can be quite simple, like light dependent resistor, but can be a little bit more complex, like integrated circuits with built-in sensor and making some reading by itself, making the conversion by itself. So let's start with simple sensors. One of the possibility is to use photodiode. Photodiode is the normal diode, so PN junction, semiconductor junction, that has such window, glass window, that allows us to put the light onto the silicon itself, silicon chip. We have two different versions. One is named PIN photodiode, so this is the cheapest version and very popular. The second is avalanche. Avalanche photodiode even increases current by reaching avalanche breakdown reverse voltage, but it's more expensive and it's not so popular as PIN photodiodes, but you know, the mode of operation is almost the same in photoconductive mode. Photodiode can work in two modes. Photoconductive, so it works in reverse bias, so it means the voltage that polarizes this photodiode is connected in reverse, so plus to cathode, minus to anode, not like normally in diode in opposite direction. And because of the light that lights the PN junction, the reverse voltage or reverse current is modified by this light. In photovoltaic mode, it works slightly different. It generates the voltage. So photodiode can work like we can say something like a similar photovoltaic cell, and it generates the voltage that we can measure. But the most often used mode of operation is photoconductive mode, and in this photoconductive mode the photodiode should be connected like in the schematic diagram. So we have the resistor that polarizes our photodiode in reverse connection. Yes, so anode it's connected to the ground, cathode is connected to this polarized resistor, and here we can measure the voltage of the photodiode. Notice that if the light is stronger, the current is also stronger, bigger, that goes through this diode, so the voltage drops. Okay, in this connection, if the in complete darkness the voltage will be higher, in light condition the voltage will be lower. Another element that we can use to measure the light intensity is phototransistor. Phototransistor, similar like diode, we have the enclosure with the glass window, and the light comes through this window onto the base emitter connection, a base emitter junction, and it works like base current. So it is amplified by this transistor. So we can say it introduces additional gain. So even smaller amount of light energy creates bigger reaction on the output, but phototransistors are slower than photodiodes. So they amplify the signal, but they are slower. A phototransistor can be connected in common emitter connection or common collector connection. In common emitter, if the light is higher, the voltage that we can measure here is lower. In common collector connection, if the light is stronger, the voltage rises. Another element that can be used as the light sensor is named LDR, so light dependent resistor. This is also a semiconductor element, but without p-n junction. So it works rather like resistor, with the resistance that changes depending on the light condition. If the light is bigger, the resistance of this element is smaller, and of course in complete darkness the resistance is much higher. In dark, the resistance of photoresistor can rise up to mega ohms. In the strong light it can be as low as few hundred ohms. They are much slower than photodiodes, they are slower even than phototransistors, but if we do not need the high speed, we can use photoresistor. They are quite cheap. Unfortunately, they are also temperature sensitive, so not only the light condition influences their resistance, but also temperature. Connection of LDR is similar like connection of photodiode. Like here we have photoresistor or LDR connected to the ground and polarizing resistor to the power supply, and we can measure the voltage here that drops in the strong light conditions. Because photoresistor doesn't have p-n junction, it doesn't matter if we connect it, the direction of the connection is not important. Another possibility of color sense of the light sensor is the RGB color sensor. This is much more complex element because this sensor is here at the middle, in the middle of the board. This is of course not the sensor only, but also element that measures the light and converts the analog signal to digital version, and also encodes this into some digital protocol. As you can see here, we have I2C interface, so some special digital serial interface that we can read the data using microcontroller from the sensor, and we obtain the information on the red color intensity, blue color intensity, green color intensity, and the common intensity. Yeah? Additionally, we have here LED that we can turn on and measure the reflected light. So not just the light, ambient light or generated from some other sources, but also reflected light from some surface. The symbol of this chip, of this board, is TC34725. A connection of this sensor is made like this. For example, here we have the board based on ESP32. Here we have the sensor, and we connect LED that controls this LED on board to some pin. We can also connect ground, power supply, and the most important two lines that we need to connect are SDA and SCL. SDA, this is serial data. SCL, this is serial clock lines, and these two lines are responsible for the communication between microcontroller module and the sensor. And of course, we can download the library. There are a lot of different libraries for different sensors, for different frameworks. So, for example, for Arduino, we have library that allows us to read the current readings of such sensor. Another interesting element that is available on the market is a gesture sensor. It is based, for example, on the chip named APDS9660. This is this one chip, and this chip allows us to read the light conditions like RGB intensity of red, green, and blue light, but also it recognizes simple gestures, because as you can see here we have two holes. Yes, one is the LED that generates infrared light, and the second is the sensor itself, and we can, moving our arm or our palm before the sensor, left, right, up, down, we can have the information about the last gesture that we made. This is quite nice possibility, and simple detection of simple gestures. It is also connected using the similar interface as the previous one, so we need some additional software library to read the data from the sensor. Sensor based on infrared light or changes on or infrared light named PIR, passive infrared light. It checks the changes in infrared sources in the environment. For example, it can detect movement of person, because human body generates infrared light, generates heat, so it can be observed using infrared sensor, and this lens here allow to detect movement of this infrared source, and in such situation we have the information about detection of some object generating heat moving at the front of the sensor. It has digital output, so we have information, yes, there is a movement and there is no. This kind of sensor is very often used in surveillance monitoring systems. There is also interesting sensor named GridEye. The GridEye sensor is the matrix of infrared sensors in 8x8 configuration. So we can say we have such simple infrared or thermal camera that gives us such picture 8x8 pixels. It has I2C protocol to read this data. Of course, we read 64 bytes for every frame. It is used mainly in detectors of moving persons, but without, or maybe not only moving, but also what is the current pose of the person without without affecting their personality, because it's not possible to detect who is this person, but we can observe what is this person doing. Another set of sensors will be temperature sensors, and here we also have different possibilities to measure temperature. We can use simple element named thermistor. We can use thermocouple. There are two metals connected together. We have something that is named resistance temperature detector. This works similar like thermistor, but has a higher temperature range. We can have integrated circuit that is created as analog thermometer, and also we can have digital thermometer. Let's start with thermistor, so element that measures temperature in similar way like light dependent resistor. Yes, it changes its resistance depending on the temperature, and we can have two different versions of such thermistors. One is named NTC, second is named PTC. NTC is negative temperature coefficient, so it decreases resistance while temperature rises, and the other is PTC is positive temperature coefficient, so it increases resistance with increasing temperature. Both have the same symbol, and both are similar in the maybe not in the construction, but in the appearance. So you need to have the documentation what is the kind of thermistor, and this can be connected very similar way like LDR. So for example, like in this schematic diagram, here we have thermistor connected between the ground and the analog input of Arduino board, and of course we need some polarizing resistor to the power supply. And if this thermistor is NTC, so if the temperature rises, its resistance lowers, so the voltage also drops. Another element, thermocouple. This is electrical junction with two conductors, usually two metals. And what is important here, such thermocouple can have bigger range of temperatures, and it can it is resistant to very high temperatures, like for example 1700 Celsius degrees. So they are used in ovens and similar places. There is also RTD, resistance temperature detector. It also has quite wide range of temperatures from -200 up to +500 Celsius degrees. And the example of this detector is symbol, it's PT100. This 100 means it has 100 ohms in normal ambient room temperature. Both such PT100 and thermocouple signals should be amplified. So normally we use such bridge of resistors and operational amplifier to amplify the signals, because these changes in the signals or in the resistance are quite small. So we need the bridge connection and operational amplifier to obtain the voltage dependent on the temperature, and this voltage we can measure using analog to digital converter. I told you that there can be also whole integrated circuits that measure temperature, and there is analog example of such thermometer with the symbol TMP36GT9Z, quite complex symbol. It allows to measure temperature from -40 up to +120 Celsius degrees, and the voltage change at the output is 10 millivolts per 1 Celsius degree. It has analog output, so we need to measure this analog output with the analog to digital converter. There is also similar looking chip, but it is digital thermometer, very popular in students' projects. DS18B20, this is created by Dallas Semiconductors, and it has special communication protocol called one-wire. And this one wire allows us to read the data from this thermometer using just connection the ground and one wire from this element to microcontroller, and using this another line we can also provide power supply to this chip. So it has 3 outputs because it also has power supply pin, but we can connect this power supply pin through the resistor to the data line, and using 2 lines we can transmit data from our microcontroller, from the thermometer to our microcontroller. It allows us to read the data from -55 up to 125 Celsius degrees. Very, very popular chip, mounted in many different variety of devices. All the group of sensors are created using very small mechanical elements. The common name of such sensors are MEMS, so micro electromechanical sensor. And because we have internally some mechanical elements, we can measure different phenomena, physical phenomena, that are connected to some movement, rotation, magnetic field, for example. So the sensors that we have in this group are magnetic field, compasses, accelerometers, gyroscopes, something that is called IMU, inertial measurement unit, and depending on the construction, we can have analog output or digital output from such sensor. And some examples of such sensors. First, let's start with compass. Compass, we can say this is 3-axis magnetometer. And this symbol of this element is L883. It has digital outputs, 3 axes, and you can see on the boards how these axes are here directed. Yes, so the x-axis is here, y-axis is here, and z is through the board. Yeah. Here we have I2C interface. So the similar interface that we talked about, for example, this RGB sensor. There is also version named ADXL3 with different numbers, and this is analog version of such compass. So we have 3 analog outputs, and we have to measure voltages on 3 channels with our microcontroller if it's capable to do it. Another element that we can use is accelerometer, very often used in, for example, measuring the accelerations of I don't know, car toys or something like this, for example, in drones also. This one is named MMA8452. It is 3-axis accelerometer. As you can see here also, we have the information about the direction of the axis here, and also has I2C interface, and it's possible to read the data using digital interface from this accelerometer. Another one is gyroscope, based on the LSM9DS1 chip, and it is IMU module, so inertial measurement unit module. And this inertial module measures, we can say, 9 different parameters. So it has 3D magnetometer, so like in compass. It has 3D accelerometer, so measures accelerations in 3 axes, and also 3D gyroscope, so it measures rotations in 3 different axes. Yeah, so this is I think most universal. You need to measure different aspects of the movements, I don't know, of arm, for example. Yes, it can be used for drones, it can be used for the arm of the robot or something, some similar applications. This one has also I2C interface. As you can see, I2C interface is very often used in such applications. Another group of sensors, environmental sensors, so some sensors that measure not only temperature but also some other parameters of our environment. They can measure air pollution, humidity, air pressure, and of course temperature also. Very popular now, sensors for measuring air pollution. They use the special laser sensor inside that can measure the particles that are passing at the front of the sensor. Here you can see such rounded shape. This is the inlet of the air, and it is equipped with the fan. Such small fan there is inside that ensures the constant flow of the air inside the sensor, and in such situation it can calculate what is the number of particles of different sizes and give us the information about groups of particles, for example PM1, PM2.5, PM10. This sensor uses UART interface for the data transmission, so not I2C but normal serial port, so we can connect it even through some voltage converter to our PC computer or through USB converter to our PC computer and have the information about the current air pollution. Very popular sensor for humidity and temperature. This is DHT11. There is also version DHT22, very similar but white one. It has special interface that has similar rules of operation like the one wire that we talked about during this Dallas temperature sensor, but it's not the same. This is similar but not the same way of transmission. It also uses one line to transmit data, but it requires different library than this Dallas sensor for measuring temperature. There are air pressure sensors, different air pressure sensors. The example BME280, it also measures pressure and temperature. This temperature measurement comes from such phenomena or from such situations that in many cases this pressure and humidity sensors are dependent also on the temperature. The readings are dependent on the temperature, and sometimes they have built-in compensation of the temperature. So that's why this temperature is just also measured and is sent as the result. This one measures pressure, air pressure, and also temperature and sends the data with I2C interface. Another one can measure air pressure, temperature, and humidity with one sensor. The name of it is BMP085, and it has different interface. It has SPI interface. Some of them can use both interfaces depending on the connection on one pin, but this one allows us SPI, and you can see here the names SCL, SDA, so I think it supports both methods of communication, SPI and also I2C. We can measure also not only particles in as the air pollution, but also some gases. So there is big group of different gas sensors. They look similar because they their mode of operation is similar, and they can detect maybe group of gases, maybe only one of them, depends on the sensor. So I just show one of them. but we can detect carbon dioxide, carbon monoxide, hydrogen, methane, alcohol, and many others. This one has analog output, so we have to measure with the analog to digital converter what is the output voltage of the sensor. It has also digital output, but from internal comparator. So we can set, using potentiometer, we can set what is the voltage level that should be, for example, used for alarm. And we can have such information, digital information, but not about the level, but about that the current situation rises above the threshold. We can have sensors for measuring other physical parameters, like, for example, weight, like distance, position, and magnetic field, not only with magnetometer, but also using some other effects. For pressure and for weight, we can use tensometer. Example of tensometer is here. It changes the resistance very slightly, so we need to amplify it, and normally we use the bridge connection and operational amplifier to obtain the results from tensometer. We can have proximity sensors. This one is ultrasonic proximity sensor. We have here ultrasonic transmitter and ultrasonic receiver, and normally we generate short pulse on the transmitter and observe what is the propagation time of the signal for and back between transmitter and receiver. So it requires 4 wires to be connected: power supply, ground, and one to start the signal, and second to receive the signal back. Another proximity sensor uses the infrared light. As you can see here, also we have transmitter and receiver. Transmitter generates the infrared light, and the reflected light is observed by the receiver, and basing on the intensity of the light, we can estimate what is the distance between our sensor and some object. We can also try to find out what is our current placement on the Earth using GPS sensor. It uses satellites, of course, so it must be in the visibility of satellites, uses global positioning system, and the data here is available using special protocol that is called NMEA. This protocol uses normally the serial port connectivity, so UART, for receiving this data. And magnetic field sensors. This one here is very simple, is known as reed switch. It just has 2 metal elements that connects together in the presence of a magnetic field. If there's no magnetic fields, this internal switch remains open. So that just gives simple information, 0 or 1. There is a magnetic field or not. But we have also a sensor that uses the Hall effect. The Hall effect changes the intensity of output voltage depending on the intensity of the magnetic field, so we can measure it using the digital converter. Such sensors are very often used for rotation position detection in motors, in, for example, engines, in motors, in hard drives. So we can also use them to detect magnetic field. And to such sensors we can also include touch panel that can cooperate with some display, but it can also be some standalone element that detects the place where we put our finger. Normally it operates as as the resistors that we can connect together, and to detect the place in X and Y axis, we need to put the voltage, for example, here in these two electrodes, and measure the voltage here, and to detect the opposite axis we put the voltage, we put the voltage here. Oh, doesn't work. Put the voltage here and measure the resulting voltage here, and we obtain the two axes X and Y, and that's why we can detect the position on the screen or on this sensor. Dear students, this time we'll talk about actuators. So how to influence the parameters of the environment, how to signal something, how to show that something should be shown in our IoT system. We can say we have some output devices. Yeah? Sensors we could treat as input devices. Actuators we can treat as output devices. And output devices, I think, is more general term because it shows that something happens at the output, not necessarily make some movement on some action like exactly actuators does. So this output device is the electronic element or electronic system used for giving some information to the user. It can be also used for controlling some actuator or control some other subsystems. Let's start with visual output elements because they are, I think, quite popular and very easy to be used. So just look in the details and some examples of the elements that we can use to show something. Of course, in modern applications, the most popular element to show something visually is LED. It can be controlled directly from a microcontroller, from microcomputer system on chip, because it doesn't consume a lot of energy, it doesn't have special power requirements, and of course we can have LEDs that consume more power, that needs a little bit more power because of the light intensity, and in such situation we can control them with some additional amplifier, like for example simple transistor. What is important, you need to remember that every LED needs the limiting current resistor. If you don't provide this resistor, you can burn LED, you can also damage your chip. So please always use a limiting current resistor. Of course, there are some situations why this resistor is not needed if it's built in the LED. Yeah, but if you have such ordinary LED, it usually needs some limiting current resistor. This is example of the connection of the LED. Here is this light emitting diode, the current limiting resistor, and the voltage source like output of our microcontroller. We can obtain on the market variety of different LEDs. They can be single colored, they can be multicolored. For example, multicolored LED that contains three elements, three different chips, light emitting chips, can be RGB LED, and this chips here, because you know LED has, every diode has anode and cathode connectors, so this LED in one enclosure, three LEDs in one enclosure, can be connected in two different ways: common anode or common cathode. It looks like this. If we have common anode, like here, all anodes of the internal LED chips are connected together, and cathodes are provided as the external pins. So in such situation, we connect common anode to the power supply, and using limiting current resistors, two outputs of our microcontrollers. If we have common cathode LED, we connect this pin to the ground, and through current limiting resistors separate anodes to outputs of our controllers. Remember that it's not good idea to connect just single resistor here, because different colors have different requirements of voltage and different requirements of the current. So it's much better to connect separate resistors for every color than one common resistor for all LED. Another possibility to have multicolored LED are LEDs with built-in controller. In such situation, we have to provide them the power supply, but we do not need these limiting current resistors because they are built in. So here you can see this stripe of 8 RGB LEDs that are digitally controlled. So you connect power supply to 2 pins and the input from microcontroller that sends in digital way the information to all LEDs here, and these LEDs can be controlled separately. So for example, one of them can be lit in red, second in blue, last in green, and another 2 colors simultaneously, and even you are able to modify the intensity of every color. So you can obtain here very interesting color effects using such digitally controlled LED. They are controlled in series, so you need to remember that if you connect many such LEDs together, you can observe the delay of sending data from the first to the last LED. But here is just 8 LEDs, so this communication goes quite fast. LEDs can be used also to form some other bigger displays, like here. This is the example of 7-segment display that allows us to display such shapes that are similar to numbers. One digit contains of 7 segments plus 1 decimal point. So we have 8 LEDs in such one digit. They also can have configuration of common anode or common cathode. So if you make a design of the system, you need to decide if you prefer common anode or common cathode connected together. Notice here the LEDs have the same color, but you know, physically every LED is different, so every LED, every segment needs separate resistor. We can have also alphanumerical displays, like a 16-segment LED display like this. It allows us not just to display shapes similar to digits, but also shapes similar to letters. And also we can have such matrix of LEDs connected in similar way like the keyboard on the previous lecture. And of course, if we want to display something on such matrix, we need to use similar procedure for displaying. So for example, activate one row and display what do we want to be displayed on the single row. Next, switch to another row, another row, another row. Such method of displaying is named dynamic or multiplexed. So it needs the special procedure to be displayed. And what is important here, every row, if we switch rows, every row should be lit the same amount of time. If the time will not be constant between rows, we will observe that one row is darker, another row is much more brighter. There are also ready alphanumerical displays. This is example of very popular family of displays based on HD44780 controller. They display digits, letters and other symbols in such matrix of 5 times 7 points. They are based on LCD technology and they are very, very popular. different possibilities of connection of such displays we have. We can connect them using 8-bit data, 8-bit data connection, 4-bit data connection, and some of them even are equipped with I2C converter, and there are libraries written, for example, for Arduino, and we can use I2C, so 2 lines only to connect such display. Originally, we have a 8-bit data bus to connect to this display. We also need at least 2 lines, so register select and clock to store the data there. If we connect it using 4-bit operation, we need to connect 4 bits, register select and enable. This read-write pin can be connected to the ground if we don't want to read something from this display. Normally we don't, so we can connect this pin to the ground. Another possibility are graphical displays. Quite popular display, monochromatic display, comes from popular few years ago mobile phone, the Nokia 5110, and this display is very popular among students. It allows us to display pictures of the resolution 48 times 84 pixels, black and white only, SPI connection, so we can connect it using 4 wires to our microcontroller and display different graphic information. If we need more information, we can use TFT color displays. This is example of such color display. This one has 1.4 inch and it has resolution 108 times 108 pixels, RGB of course, connected also using SPI connection. It has built-in controller, so it makes communication much easier. It allows to write text, draw some shapes, and this is quite easy to be used. Of course, there are libraries for both displays written for different frameworks, for example Arduino. There are also bigger displays. This is twice bigger as the previous one, also based on TFT technology, 240 times 320 pixels with built-in controller, and this one I show here is compatible with Raspberry Pi. As you can see, it has such connector here that fits exactly into connector of Raspberry Pi, so we can connect it to this microcomputer and use it as the, we can say, even main display. Additionally, here you can observe the 4 wires that are outputs of the touch panel that is mounted on the top of this display. So we have display and additionally touch panel that we can use as the input to our microcontroller. New technology of displays, organic LED, so OLED, they are also available for use in our microcontrollers. This one is example of very small 1.5 inch OLED display, resolution 96 times 64 pixels, SPI connection. Notice that very often here we have SPI connection. That's because SPI is much faster than I2C. So I2C is okay for reading few data from sensors, but it's not suitable for sending quite big amount of data for the displays, because if we have 100 times 100 pixels, yes, we need to send something about 10 kilobytes of data. So it's much better to use SPI because it's much faster. This one also has built-in controller. The name of this controller is SSD1331. These controllers somehow are compatible between different types of displays. So normally, if we take the library for one display, it also, after slight reconfiguration, fits another display. Sometimes we need to control some elements that need more power that can be provided directly from our microcontroller or even from power supply of our microcontroller. In such situations, we need some amplifiers, or we need some, we can say, elements that allows us, using very weak signal, like signal coming from our microcontroller, control something bigger. One of such element is relay. Relay is electromagnetical device, that this blue one here, that allows us to switch on and off the signals of the bigger power. For example, control heater connected to power mains, or control bulb connected to power mains, and some other elements. This relay is mounted on the board that has here the amplifier, because even relay itself needs more power that can be provided from the output of microcontroller. So here we have transistor driver that switches on and off this relay, and the relay is connected to this header here and allows us to connect something that needs bigger power or higher voltage. Additionally, relay separates electrically the input part from the output part, so even if we connect here something from power mains, we are safe because they are separated by the relay from our microcontroller part. These are examples of configuration of different relays. Here we have a relay that is named SPST, so single pole, single throw. We have also single pole double throw. So here you can see we have the on and off state only, and here we can switch between A and B signal. Here we have a double pole single throw, so we have two lines but on and off only, and here we have two switchable lines. Of course, these are just few examples. We can imagine that we have relays that have many such poles if needed, but these are the most popular ones. If you look at such relay, here there is no such information, but sometimes you have the information NO and NC. NO means in no voltage, if there is no voltage provided to the coil of the relay, this pair of connections remains open. NC means normally closed. So if there is no voltage provided to the coil of the relay, these two contacts are stuck together. Yes, so there is a connection between them. Very often, if we want to separate galvanically or electrically our one part of the circuit with another, we use optocouplers or optoisolators. We have different types of the optocouplers. One type is named optoisolator, and it connects in one enclosure LED diode, usually working in infrared light spectrum, and phototransistor at the output side. So if there is no current here, so we connect it as normal LED, so we can connect it directly to the output of our microcontroller. If there is no light here, this transistor is not active, we can say. Yes, it has higher resistance. If there is a light generated by this LED, transistor is in closed state, so the voltage on it is very low. So we can control some external elements using optocoupler, keeping safe our microcontroller part of the device. Optocouplers are used for controlling high power, high voltage elements, but also to avoid noise coming from external elements. For example, we can control the motor that generates a lot of electrical noise, and there is no influence of this this noise on our microcontroller part of the system. Another optocoupler is solid state relay. This works similar to relay, but it has internal element that is named triac, optotriac. So this optotriac is also in active state, in on state, if there is a light generated by LED, in off state, but while the LED is off. Solid state relay internally can be built on triacs, but also on MOSFET transistors. This is schematic diagram of connection of optotriac and the normal triac to control some high power elements, like for example, or high voltage elements, like for example bulb, or maybe heater, or maybe some other element connected to power mains. Notice that this element ensures galvanic separation of the danger voltage here and our microcontroller part at this left side of our schematic diagram. And additionally, some of these elements has such nice feature that is named zero crossing detection. Zero crossing detection means that even if we put the voltage here, for example, during the active part of the sine signal, it will not switch immediately on, but it will switch on while this voltage crosses zero value. This prevents of additional electrical noise from generated from this high power output device. Another high current element that we can connect to our IoT system is something that generates noise. This can be buzzer, this can be speaker, for example. Usually, to generate the noise that is not very quiet, we need quite a lot of power that our microcontroller cannot provide. That's why we use some amplifying element, like on the schematic diagram, simple transistor connected to port of our microcontroller. And here we have, for example, buzzer or speaker, electromagnetical speaker that we can control using this transistor. This transistor allows us to connect something that consumes few hundreds of milliamperes even. So that is much too big a value for output of our microcontroller, because normally microcontrollers can give us something about, or can source something like 20 milliamperes maximum. This is example how to connect relay to our microcontroller. Similar connection and on previous slide. Here we have output of our microcontroller, limiting current resistor that limits the current that goes through base and emitter junction of our transistor. And here we have the relay that is controlled by transistor, and of course here we have the output circuit, and we can, using this output circuit, we can connect something with higher voltage and higher power. We can also use MOSFET transistors that are much more popular at the time. They have better power properties, we can say, because they have smaller heat generation. They can control higher current at the output than normal bipolar transistors, but they are slower. So this is what we need to remember, that because of their construction, they have better in heat dissipation in power conditions, but they are slower than such normal transition like from previous example. But of course they are very often used in modern circuits. If we want to control motor, we can use such H-bridge connection. This H-bridge controls transistors in pairs. So, for example, this signal, right, enables this transistor and this transistor. So current goes from plus through this transistor motor to the ground. If we activate left, the current goes through this transistor motor and to the ground, so the motor is polarized in opposite way. So the direction of the motor is opposite. What we need to here take care about, do not switch on both these signals, because you know it will create short circuit between power supply and the ground through all 4 transistors, so we can burn transistors out. We can have also analog outputs, because till this time we were talking about digital outputs to different actuators. We can also have analog actuators, like for example speaker. And to provide analog output, we have 2 different possibilities. One possibility is to create the voltage, the variable voltage, using digital to analog converter and connect this converter to the speaker, the similar way like we had in the previous examples. But this needs the linear amplifier, and this is not very often a method used in modern microprocessor systems. It's much harder to obtain the, or to maybe not to generate the analog signal, but to amplify it and using in modern electronic elements. The method that is commonly used to generate different both analog audio signal, maybe not both, all analog audio signal, rotating speed of motor, intensity of light, and many other parameters that can be generated by actuators, is using PWM signal. PWM signal is the signal that has stable frequency, but the length of the pulse differs depending on the average power that we want to provide to the output. So if we have very short pulse, if we connect, for example, it to LED, the LED will be darker. If the pulse will be longer, the average power that we provide to the LED will be bigger, and our eye will observe it as the higher intensity of the light. That's why the PWM modulation is very often used for controlling light intensity, speed of motors, audio signals, and such purposes. Okay, so now we know, I think, enough about electronic elements, about from previous lectures about microcontrollers, about microcomputers that we can use in IoT systems. We know a lot about sensors, we know a lot about actuators, so next time we can try to start writing programs and obtaining some interesting systems and nodes. Thank you very much for today.